Okay, so we've already looked at one sample and two sample hypothesis testing for a population proportion, so let's spice it up for a population mean. We're aware that confidence intervals are one of the two most common types of statistical inference, and our goal for an interval is to estimate a population parameter. The second most common type of inference is what we call a significance test. This is a formal procedure for comparing observed data with the claim, which we call the hypothesis. And this is the truth that we're trying to assess. The claim is a statement about a parameter. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree, assuming the null hypothesis is true. And this is the statement that's being tested. The significance test is designed to assess the strength of the evidence against the null hypothesis. And usually the null hypothesis is a statement of no effect, no difference, or no change from historical values. Now, what we are trying to find evidence for is what we call the alternative hypothesis. Usually this is a statement of an effect, a difference, or a change from these historical values. Now, to assess how far the estimate is from the parameter, we standardize the estimate using the general formula, sample minus parameter over the standard error. But here, for our means, we're going to use our sample mean minus the claimed population mean. And then again, we usually don't know the population sigma, so we'll use our sample standard deviation to estimate sigma, and we'll divide that by the square root of n. And this looks very familiar to our sampling distributions for a one sample mean. And in case you ever forget these formulas, I'm pulling it up on my formula sheet. Here we go. For one population means, here are the parameters. So here's the standard error, which you'll need in your denominator. Here is your claimed parameter, which is what you'll need for the right-hand side of the numerator. Alrighty, so after we've standardized that, the p-value is what we're evaluating. And this is the probability that we would get the sample result, or one more extreme, if the null hypothesis is true. And remember, that language of if, given, or assume turns it into a conditional probability. So, the smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. Basically saying that this result is so unlikely to occur by chance alone, we call it statistically significant. Now, if it's small or smaller than alpha, we say it's statistically significant. And in general, we use an alpha level of 0.05 unless otherwise stated. Assuming the null hypothesis is true, and we'll state that in context, the probability of obtaining our sample or test statistic, or more extreme, is blankety blank. Now again, we have two types of tests for hypothesis testing. We have a one-tail test and a two-tail test. Now the direction of the one-tail depends on the alternative hypothesis that you're testing. Is it less than? Is it greater than? A two-tail test is just suggesting that you're noting that there is some difference from the historical values. And you can see there that we can just multiply 2 times the probability that it's greater than or less than, because those shaded areas would be approximately equal to one another. Again, assuming the null hypothesis is true, each of these distributions here would be centered at the claimed mu. Now, if we are wanting to test significant evidence about a population mean, we are going to use our phantoms model, where mu is the true population mean of something happening. The null hypothesis is the claim. The alternative is what we're testing for. Alpha is stated in the problem, but if not, we'll use 5%. Our conditions remain the same, stated random, independent, normality by one of these 3 criteria. If our conditions are met, we use a one sample t-test for a mean, and we will standardize our test statistic. We now do have to include the degrees of freedom because there's more variability in testing a mean. We'll obtain our p-value using one of our probability statements. And then I actually messed up on the inequalities here. Oh no, I fixed it. If the p-value is less than alpha, we reject the null because we have convincing evidence. Or if the p-value is greater than alpha, we fail to reject the null because there is not sufficient evidence. And when we state the conclusion here, this is usually done in favor of the ha or the alternative. So do we reject the null because we have evidence towards the alternative, or do we fail to reject the null because we don't have sufficient evidence to claim the alternative? So that's just a little bit of knowledge there. So let's go ahead and take a look at an example here. Oh, lost my face. Okay. A state study on labor reported that 1/3 of full-time teachers in the state also worked part-time at another job. For those teachers, the average number of hours worked per week at that part-time job was 13. After an increase in state teacher salaries, a random sample of 400 teachers who took who worked part-time at another job was selected. the average number of hours worked per week at the part-time job for the teachers in the sample was 12.5 with a standard deviation of 6.5. Do we have convincing evidence that at the level of alpha is 0.05, that the average number of hours worked per week at part-time jobs decreased after the salary increase? Okay, so what I want you to do now is the first half of this inference procedure. Very similar to what happened when we did it for 1 and 2 sample proportions. We're going to identify our parameter, claim a set of hypotheses with the significance level. We're going to check our assumptions, and then we are going to name our test. So let's go ahead and take a few minutes now to ensure we've got the basis of our criteria or process down. And so here is the question so that you can look at that as you're working. Good luck. So go ahead and pause the video and try it out. Okay, so hopefully your paper looks something similar to this, or if you do the cross sections or however you set up your paper, let's go ahead and check the first 4 sections here. So here we're trying to find statistical evidence for mu, which is the true average number of hours worked per week at part-time jobs by teachers. And as a teacher who also has a few side hustles myself, I can guarantee this is very much a real issue. The claim is that teachers are working an average of about 13 hours, but we're trying to see, after the salary increase, did that average number of hours decrease? So I'd be testing for a less than inequality here, and I'm going to use a significance level of 5%. Now, in order to conduct my procedure, I need to check a few assumptions, and they were stated that we use a random sample of 400 teachers. I can definitely assume that 400 teachers is less than or equal to 10% of all teachers who work part-time jobs. That's only about 4,000 teachers, most definitely. The normal model here is appropriate by the central limit theorem, since our sample size of 400 is greater than or equal to 30. Now, since our conditions are met, we're going to use a one sample t-test for a population mean, or for mu. And here is now where we do the math. And by math, I mean we just kind of set it up in the calculator. We are going to check our x bar minus our mu over the standard error. So here our sample had an average of 12.5. We're seeing how far away that is from the claim, assuming a standard error of 6.5 divided by the square root of 400. Now, if you type this into your calculator or you do it by hand, you should get approximately negative 1.53. Okay, I'm going to move my face here. And next we're going to check the p-value. And here, the degrees of freedom are going to be 400 minus 1, so we have about 399 degrees of freedom. So the probability that our test statistic is less than negative 1.53 with 399 degrees of freedom is approximately 0.0623. And actually, that's kind of ugly. I do not like, so let me rewrite that. Here we go. It's about 0.0623. Now, by chance alone, there's about a 6% chance, assuming that the average number of hours worked by teachers is 13. The probability of obtaining our sample statistic of 12.5 is only at about 6%. Not too convincing, and only because our alpha level here is 5%. We were trying to find statistically significant evidence, but compared to that alpha level, it's not. So if maybe I was using a rejection region of 10%, I'd be okay. But here, I actually don't have sufficient evidence to claim this is true. So that means, since our p-value is low, and this is, oh no, it's not low. Let's do this together. How about that? So here, we would say something like, since p-value equals 0.0623 is greater than alpha at 0.05, we fail to reject the null hypothesis. And we fail to reject because actually there is not sufficient evidence to claim the true average number of hours worked at a part-time job by teachers has decreased after the salary increase. So we don't have enough evidence to verify that the salary increase actually did help us out here with the number of hours that teachers were working. In fact, there's just not sufficient evidence. There's about a 6% chance this would happen, assuming that the claim is true that teachers are working about 13 hours at their part-time jobs currently. So a fun little, not a fun example, very tragic example of some things that your teachers are enduring. But here we have some follow-up questions that are a little bit non-traditional for hypothesis testing, because the fact of the matter is that on the AP exam and in statistics in general, we're not always going to ask you to infer. Sometimes we're going to just give you the information and we're going to ask you to analyze it. We're going to look at scenarios, etc. So here, let's suppose that a test of the hypothesis of the null is that mu is 0, and that the alternative is that mu is greater than 0, and we use a sample size of 7. The test statistic was 1.935. Which of the following is the closest to the p-value? So that one is a calculator question. Here we have a situation that a statistics class from a high school with 4,000 students took a survey for the first 35 minutes, or the first 35 students who walked through the front door of the school, and asked how far they traveled to school that day. The class plans to run a one-sample t-test to determine if the average travel distance has increased since last year. The students notice that the sample data are right-skewed, which conditions have been satisfied. So here we have our random, our independent, and our normality condition. Let's go ahead and look over that. And then here we have another situation where we obtain a p-value of 0.045, and which of the following would be the most appropriate conclusion using this significance level. So take a snapshot, take a picture, or if you're working in your notes, go ahead and attempt these problems. Pause the video, and then we'll go over them in a brief moment. Okay, so hopefully you were able to work through some of these examples, but if we use a t-CDF in our calculator using degrees of freedom 6 here, the probability of obtaining a sample statistic as large, if not larger, than 1.935 would be about 0.0506. And depending on our alpha level, we would either reject or fail to reject the null hypothesis. Next up in this situation, again, huge shout out to StatsMedic for always just having great resources. But here, we did not use a random sample. We used a convenient sample since we took the first 35 students who walked through the front of the door. These students were easiest to reach, and perhaps they were coming to school early because they have a further commute and they have to over-plan their commute time. Now, this is a common fret on the AP Stats exam because they notice that their sample data is right-skewed, but their sample size is 35. Now, our hierarchy here of normality says the population must be normal. That's not the case here. The central limit theorem applies, which is that the sample size is greater than 30. Now, here's why the sample size is going to outrule this right skew. Because of this sample size, if I were to take all possible samples of 35 students from these 4,000 students, my sampling distribution for the mean would become approximately normal because of the sufficiently large sample size. Now, if I did not have the sample size and I was just told that the sample data was right skewed, then the normal model would not be appropriate. But here it is appropriate since this large enough sample size will give us an approximately normal sampling distribution. And then lastly, the sample size is small relative to the population. Checking our 10% rule, we see that yes, 35 is most definitely less than or equal to 10% of these 4,000 students. And then lastly here, this claim for this small town college, your null and alternative hypotheses would look something like this. It appears as though we're using an alpha level of 0.05. And because our p-value, assuming that this is the true starting mean, the probability of obtaining our sample statistic, or more extreme, is about 0.045. And since the p-value is low, lower than the rejection or significance level, probability of making a type 1 error, we can reject the null hypothesis because there is in fact some evidence that would suggest that the alternative hypothesis has some credibility. So that's going to do for our study on one sample t-test for means. And make sure you practice using the homework and the other material in the module, or if you've just stumbled upon this video on your YouTube search, then I hope this has provided some type of insight for you.